Welcome to a new RKB Bearing Industries educational video where we show the functioning of one of the proprietary in-house developed software tools used by our technical department, the RRLC or RKB Rating Life Calculations, whose main objective is to provide users in a time-efficient and accurate way with consistent background of relevant data for the selection of bearing size in relation to the applied loads, lubricant influence, and the requirements regarding service life, reliability, and safety index following the rules defined by ISO 281 in the latest revision. The term basic rating life means the fatigue life exceeded by 90% of the bearings or the time before which 10% of the bearings fail. This basic rating life is referred to as the L10 life, sometimes called the B10 life or 10% life. Palgrim first proposed this definition of bearing life in 1924. Today, this is the universally accepted definition for bearing life calculations. As far as it can be determined, it is maybe the first probabilistic approach to life prediction of machine elements. The life of bearings depends on several variables, the most important of which are the loads and the speeds. In case of an application where these parameters are known, a fast way to predict the bearing life is to calculate it using the equation for the basic rating life L10, where C, the basic dynamic load rating, is defined as the load that a bearing can endure for 1 million inner race revolutions with a 90% probability of survival. Capital P is the equivalent bearing load, and lowercase p is the load life exponent. Modified rating life L10M is a more reliable method to calculate the bearing life. According to ISO 281, this method evaluates the bearing life by using the life modification factor, AISO, and the life adjustment factor for reliability, A1, that are dependent on the type, size, and internal geometry of the bearing, the manufacturing quality, the fatigue limit of the raceway material, lubrication method, type of lubricant, viscosity, additives, cleanliness, and filtration, operating temperature, and bearing speed. The life temperature dependence graph is presented along with the influence of the contaminants on the bearing life. If a bearing is properly designed, lubricated, operated, and maintained, its service life is limited by the fatigue of its components. In a classical sense, a crack initiates in the subsurface zone of maximum shearing stress below the running track of the raceways and propagates towards the surface, and becomes a pit or spall that is initially limited in area to that of the Hertzian contact area and to the depth of the maximum shearing stresses. The time it takes for the first spall to occur is the measure of the bearing life. By way of example, in this educational video, we are going to describe the use of the RKB Rating Life Calculation software for a 4-row taper roller bearing, type TQ0331157A2HA1ZBBT4B for rolling mill application, following the customer requirements with particular attention to the ISO method for calculating the basic rating life and modified rating life. In order to run the RRLC software properly, it is necessary to select the bearing type, number of rows of rolling elements, and to insert the main characteristics of the bearing such as the inner ring bore diameter, DI, outer diameter of outer ring, DO, pitch diameter of rolling elements, DPW, the basic dynamic radial load rating, CR, and basic static radial load rating, COR, previously calculated by the RKB MTDS software following the rules defined by ISO, and the contact angle alpha. In order to determine the inner ring shaft fitting and the outer ring housing fitting, the diameters and deviations of the bearing, housing, and shaft are inserted. The temperature difference between the inner ring and shaft and outer ring with housing are inserted in order to determine the working clearance. According to the customer specification for the application, the bearing is subjected to variable operating conditions, where load varies in magnitude over time with changes of rotational speed. In order to calculate the bearing life, it is necessary to compute an intermediate step related to the variable load conditions. In this case, it is required to reduce the load spectrum of the application to a limited number of simple load cases, in our case equals to 3. Then the software calculates each case individually and applies the time fraction step to satisfy the multiple load condition. Heavy loads generated by shocks and overloads diminish the bearing life at a faster rate than the normal load regime. Even if the occurrence of these loads is relatively rare and limited to a given operating time fraction, they must be considered. The operating temperature is inserted in the software together with the type of lubricant and filter type. From the software interface, the 3-step iteration button is selected, and each step is inserted as an individual working condition case. The data for the first operational step is inserted. The radial and axial forces in kilonewtons, the rotational speed in RPM, and the time fraction in percentage. The first step is executed, and the calculated values according to ISO are filled in the first subarray table. All the parameters that influence the rating life calculations are displayed in the software interface, including actual kinematic viscosity at the operating temperature, reference kinematic viscosity required to obtain adequate lubrication condition, contamination factor, safety factor, and life modification factor. In the same way, the next 2 working condition cases are considered. After each iteration was analyzed and information stored in the data review table, the software applies and solves the intermediate step related to the variable load conditions, displaying the basic radial life and modified rating life for the studied case. The results are exported as a data report, containing all the iterations and computational information. In order to sustain the correct implementation of the ISO method without using empowered factors or formulae, the RKB rating life calculations software provides an explicit report containing all the mathematical background. All the data regarding the bearing type and application requirements are displayed on the second page. From the maximum line speed and the roll diameter provided by the customer in the technical specification, the bearing rotational speed is calculated. The next 22 pages of the report contain the explicit calculations based on the ISO method, following the variable operating conditions. The fatigue load limit, CU, is computed according to ISO 281 and is defined as the load below which, under laboratory conditions, no fatigue occurs in the material, or the load at which the fatigue stress limit just reached the most heavily loaded raceway contact. This load depends on the pitch diameter of the rolling elements and the basic static load rating. The reference kinematic viscosity required to obtain adequate hydrodynamic lubrication conditions is calculated for each of the 3 cases, its value depending on the rotational speed of the bearing. The reference kinematic viscosity diagram is presented in Figure A. The viscosity ratio, K, is an indicator of the quality of the lubricant film formation. The viscosity ratio is then calculated for each case using the value of the actual kinematic viscosity at the operating temperature, whose computation requires the interpolation between two reference points with the Ubalo-de-Walter equation. Based on the same equation, we constructed a complex function which figures out the variation of the kinematical viscosity with temperature and according to the viscosity at 40 Celsius degrees. For the operating temperature, and by solving numerically this equation, where nu is the reference kinematic viscosity at the operating temperature for the most unfavorable phase of the working cycle, one obtains the minimum kinematical viscosity of the necessary oil at 40 Celsius degrees. This value allows the RKB technical department to always propose the most appropriate oil for bearing lubrication. In this case, the kinematic viscosity of the chosen ISO oil at the operating temperature is 460 square millimeters per second. Contaminants in the lubricant, even in small amounts, will severely shorten bearing fatigue life. For this reason, the contamination factor, EC, is calculated, and a graphic representation is displayed for each case. Taper roller bearings are subjected to radial and axial loads, and, therefore, the calculation of a dynamic equivalent load rating is necessary. The dynamic equivalent radial load, PR, represents a constant stationary radial load under the influence of which a rolling bearing will have the same life as it would attain under the radial and axial loads for each case, where X and Y are the dynamic radial and axial load factors. Besides dimension, on the basis of the fatigue limit life, it is advisable to check the static load safety factor, SO, that represents the ratio between the basic static load rating, COR, and the static equivalent load, POR, giving a margin of safety against inadmissible permanent deformation on rolling elements and raceways. The basic static equivalent radial load, POR, in each case is calculated with static radial and axial factors. The static safety factor is calculated with the maximum of all case values of the static equivalent radial load. The life modification factor, AISO, is calculated taking into account the load on the bearing, the lubrication condition, lubricant viscosity and type and bearing speed and size, the fatigue load limit, the bearing type, and the environmental conditions that can influence the contamination of the lubricant. Life modification factor diagram is presented in Figure D. The basic rating life L10 in million revolutions and L10H in hours are calculated for each phase, along with the modified rating life L10M in million revolutions and L10MH in hours, taking into consideration the life modification factor for 90% reliability and the life modification factor, AISO. On this page, a data review table is presented in order to have clear information regarding the influence of the application parameters on the bearing life. Next, the time fraction step is executed, and the total basic and modified rating life for the studied case are calculated. Based on the ISO viscosity grade we proposed, the modified life will be also recalculated and presented as a data review table in order to emphasize the difference in life. A correct selection of the oil for the given application will reduce the chance for a bearing to collapse, improving the working condition and its lifetime. Generally, bearings can only perform to their full capacity when they are correctly fitted on the shaft and housing. Insufficient interference on fitting surfaces could cause permanent damage in mating parts. For this reason, the RRLC software calculates the tolerance band of housing and outer ring, the minimum and maximum clearance of the mating parts, and the tolerance band of the clearance, and the mean probable clearance. Assumption of a scrap rate of 0.27% was adopted to perform the calculation of the tolerance band of the probable clearance and the range between the minimum probable clearance and maximum probable clearance. Afterwards, the same calculations were applied to the fit inner ring and shaft. As common knowledge, all the rotating elements of a bearing under load generate heat, which affects the interference fits of the shaft and housing. In order to calculate the influence of the temperature on the bearing clearance, we assume a temperature difference between the inner and outer ring of a bearing equal to 10 Celsius degrees, and a temperature difference between the operating and mounting of the shaft of 15 Celsius degrees. The temperature difference between the inner and outer ring affects the decrease of the clearance. In addition, the influence of the shaft temperature difference on the axial clearance is also calculated. Consequently, the actual working radial clearance is obtained by subtracting from the radial internal clearance the decrease of the clearance due to temperature both in radial and axial direction. Relubrication should always be accomplished at a time when the lubrication of the bearing is still satisfactory. The relubrication interval for normal operating conditions can be considered as a function of the bearing speed and mean diameter that form a complex parameter, the speed factor and the factor depending on the bearing type and load condition. In order to develop the calculation of the regressing interval, the reference radial load per phase is needed, as well as the reference speed. The relubrication interval is about 4,219 working hours. To sum up, the RKB rating life calculations is the RKB in-house developed patent-pending software system used by our technical department to provide customers with all the relevant data regarding the basic rating life and modified rating life of the bearings of a given application, computed strictly following the methods defined by ISO. In this way, we supply a comprehensive and improved information service to evaluate and select the most appropriate rolling bearings in terms of basic and modified rating life. For further information on the role played by the ISO compliance in performing bearing load rating calculations, please refer also to the related RKB seminar.